This is the first section of chapter 4 on recurrence relations, and this is forming recurrence relations. Now you would have come across this already in Pure 2, and that is in chapter 3, I believe, chapter 3 and section 7. So I'll put a link in the description to that, which is also sort of an introduction to recurrence relations. So just a reminder of what a recurrence relation is. It's a rule that generates a sequence where you need the last term to get the next term. Okay, so a recurrence relation is a rule that, or you could say even a formula, that generates a sequence by using previous. Now I'm going to put terms here and put the S in brackets because sometimes it's just like the previous term, or sometimes it's more than one term. Now that will give it a special name. So let's say we get a recurrence relation that generates a sequence and all we need is the last term. That's what we call a first order recurrence relation. So a first order recurrence relation uses the previous term to generate the next term. So we only need just one previous term to generate the next term, and it's called a first order recurrence relation. If we use the last two terms to get the next term, so a bit like the Fibonacci sequence, you use the last two terms, last two numbers to get the next number in the sequence. That's what we call a second order recurrence relation. So a second order recurrence relation uses the last two terms to generate the next term. Now I've just realized my English doesn't make any sense here. Uses the previous term to generate. There we go, that makes more sense now. To generate the next term. Okay, so let's just underline the keywords here where we've got a second order recurrence relation, and this uses the last two terms to generate the next term. So we've got first order recurrence relation, which you would have learnt about in Pure 2, although you may not have called it a first order recurrence relation, just a recurrence relation. And now we've got this second order recurrence relation. So let's look at what in general these look like. So let's say we had a first order recurrence relation, so I'm just going to write this for short. Then this is the notation we use to generate the next term. So each term is like U0, U1, U2, U3 and so on. To generate the next term, we do some function of the previous term, like this. And with all recurrence relations, we need a starting value or an initial value, which we'll call U0. So this U0 is called the initial, it's actually initial condition, And with a second order recurrence relation, so again, I'll just use this shorthand here. To get the next term, it's some function of the previous two terms. So it's some function of the previous term and maybe a different function of the term before that. So you need the last two terms. Now suppose another way of writing this would be to say un plus 2 is equal to a function of the previous term un plus 1 and a function of the term before that. So this is another way of writing the same thing. It means the same thing. We're using the last two terms to get the next term in the sequence. And the last thing we just need to know about recurrence relations, and that is if we know the general term of a sequence. So if we know the general term of a sequence, now that will be in the form, this sort of form, so un equals some function of n, okay, then we can actually check that it satisfies the given recurrence relation by using substitution. Okay, so if we know the general term of a sequence, we can check to see if it satisfies a given recurrence relation by substitution. So the key bit is the substitution bit. Okay, right, let's get into some examples. So here we've got Harry who owes £5,000, sorry, not even £5,000, £500 on a credit card that charges 1.5 interest each month, okay? He decides to make no new charges and pays off at £50 a month. Formulate a recurrence relation that describes the balance remaining on the credit card after n months. Okay, so what's going on here? So we've got this initial balance or initial value or initial condition of £500. Every month the balance is going down by £50. Okay, so we've got this constant. So balance decreases by a constant of £50 a month. Okay, we're using n to stand for the number of months, but there's also something else going on. Whatever money is left, the balance that's in his credit card is increasing by 1.5%. So we could say that the balance increases by 1.5% each month. And what we need to do is to formulate a recurrence relation. Well, the first thing I can see that the initial value is 500. So I can write down that U0 equals 500. So we're assuming that we're working on in pounds here. And if I'm turning all of this information here into a formula, I would say, well, the balance in the next month is going to be the balance in the previous month plus this increase of 1.5%. So whatever the balance was plus 1.5% of the same balance, okay, that's the increase, but we're taking off this £50 every month. Okay, so if I was to label this out, this UN is the amount owing from the previous month, this is the interest added to the previous month, and then last of all, this 50 is the £50 paid off each month. £50 paid off each month. So We can simplify this because these two can go together, and in fact we probably could have done that right at the start and just said 1.015 UN, which basically means take the previous balance and increase it by 1.5%, take off the 50, and then we need to state the initial condition here, which is U0 equals 500. Okay, and just check it to see if it works. So we start with 500. So what do? We're going to increase 500 by 1.5%, then take off 50. Okay, and then we'll get some new number. Then we'll take that new number, we'll increase that by 5%, but then take off the 50. So just think through it in your head, what's going on, and see if it makes sense. Does it really answer the question? Okay, and I think this one does. So there we go. That will give us the balance remaining after n months. Okay, so here it says the deer population of a country was observed to be 1,200 in a given year. Okay, so just underline that. The population is modelled to increase at a rate of 15% each year. So this seems similar to the previous example. Let dn, okay, so we're using dn rather than un, be the population of the deer n years later. So this one is years where the previous one was month. Explain why the deer population is modelled by the recurrence relation here. Okay, so we can't start with this. We need to start from scratch and show that we get this. So the first thing is that the initial population was that 1,200. The population was 1,200. So we can say so D0 is 1,200. Okay, so we've dealt with this bit of the recurrence relation. Okay, so let's carry on with this. The population in any given year is dn, okay, which is what we're told in the question, will be the population in the previous year plus 15%. Will be the population in the previous year, and that is dn minus 1 plus 15%. So that's the same as taking a population in the previous year, dn minus 1, and multiplying it by 1.15. So that basically gives what they've asked for. The deer population in the next year is an increase of 15% of the deer population in the previous year, where the initial population is 1,200. So we've just proved that as required. So here we've got a population of bacteria that has an initial size of 200. So there's my initial condition. After 1 hour, the population has reached 220. The population grows in such a rate that the rate of growth, i.e. the number of additional bacteria, doubles each hour. We need to write a recurrence relation in terms of Bn. So before we do that, let's actually write down what this sequence looks like. So we start with 200. Then after an hour it's 220, which is an increase of 20. This question says that increase doubles. So after another hour, the increase is going to be 40, then it's going to be 80, then it's going to be 160. So that increase is doubling. That's what's doubling. So let's fill in the numbers here. So we'll have 260, 340, 500, 820, and so on. Now this is an example of a second order recurrence relation because we have two starting values, 200 and 220. So we're going to say U0 is 200 and U1 equals 220. Now the increase from one term to the next, for these two, for example, would be u1 minus u0. Okay, that's just for those two terms. But generally, if we're talking about any two terms in a sequence, we want a term, let's call that un plus 1, subtract the previous term. Okay, this is equal to the increase. Whether that increase is 20, 40, 80, 160, 320, or whatever, if we take any term and subtract the previous term, we get that increase. That increase for any two terms, like these two, for example, is going to be double the previous two increase. So the increase between these two terms, these two general terms, is going to be equal to double the increase of the sort of, not the previous two terms, but like the last two. Okay, and the last two, if we write that in terms of un and un minus 1, will be this. So I'll just go over that again. We're saying that the increase between, let's say, terms 9 and 10 is double the increase between like terms 8 and 9. Yeah, so if we just slip back one term and double that increase, we get the next increase. Now from here, what we can do is just rearrange it to make un plus 1 the subject. So if you've got un plus 1 equals to 2 un minus 1, and then add the un to both sides. From there, I can expand the brackets. I'll have 2 un from expanding these brackets here, plus the un that's there, that'll be 3 un, and then minus 2 un minus 1. Now, equivalent way of writing that is just to move the values of n, these subscripts, down one. So instead of un plus 1, I could have un, and then take this un down by 1, so I'll have 3 un minus 1, and take this down by 1 and have 2 un minus 2. So this is equivalent. Now, whichever one I use, I'll have these initial conditions, that the very first term is 200 and the second term is 220. So as I said before, this is an example of a second order recurrence relation where we need the last two terms to generate the next term. So here we have a sequence that has this general term, and the question says verify, let's make that a bit thinner, verify that the sequence satisfies this recurrence relation. Now the way that we do that, as we said at the start, is by substitution. We need to substitute this into here. And if I have a look, what can I substitute? Well, here it's un minus 1. So I need to take this un equals 3n minus 1, and I need to write it as un minus 1. Now if I take 1 away from n, this will be not 3n, so notice that that's n, that's n. So if this is n minus 1, this needs to be n minus 1. So n minus 1 minus 1. That can be simplified. So I'll have un minus 1 equals 3n, then it'll be minus 3 minus 1, so minus 4. So we do this by substitution. So this un minus 1 is going to get substituted in here. Okay, so if I put substituting un minus 1, then what we'll get is un equals 3 plus un minus 1, which is 3n minus 4, and that will give us un equals 3n minus 1, okay, which is what we started with here. So we've proved it as required. So this is how we do this type of question. Rearrange the general term into the form maybe un plus 1 or un minus 1 or un minus 2, whatever's in the recurrence relation. Substitute it in and you should get the same general term that you started with, and that proves that, or verifies that, this sequence satisfies this recurrence relation. Okay, so here we have this general term here, un equals 2 times 3n of 3 to the power n minus 1. Verify that sequence satisfies this recurrence relation. So we tackle it in the same way. If I have a look, here I've got un minus 1 here. So what I need here is this as un minus 1. Right, so we have un equals 2 times 3n, 3 to the power n minus 1. So that means that un minus 1, we just take 1 away from n, it's going to be 2 times 3 to the power n minus 1 minus 1. I suppose I could have done that all in once, pretty easy. So un minus 1 is equal to 2 times by 3 to the power n minus 2. Now we substitute this into the un equals 3 un minus 1. If we do that, we'll get un equals 3 times un minus 1, which is 2 times 3 to the power n minus 2. That can be written as un equals 2 times 3 times 3 to the power n minus 2. So this is the same as power 1, which means we just add the powers of the 3 because we've got the same base. So 2 times 3 to the power of 1 plus n minus 2. So that will give us un equals 2 times 3 to the power n minus 1, which is what we started with here. So we've proved it as required. Or we could say that the general term satisfies the recurrence relation. Yeah, so you could say this: the general term satisfies the recurrence relation. Let's spell recurrence correctly. Okay, there we go. So you should now be able to do exercise 4A on pages 123 to 125. As usual, a recap on what we've done. So we've got first order recurrence relations. We've got second order recurrence relations. So first order recurrence relation is some function of the previous term. A second order recurrence relation, I suppose if we write it like this, un is some function of the previous two terms, like this. For our first order recurrence relation, we're going to have u0, which is our initial condition. For second order recurrence relation, you're going to have u0 and u1, so you've got initial conditions. So we need two values to get us started. And lastly, if you know the general term, like this, basically like the nth term rule of a sequence, you can check it satisfies a recurrence relation by substitution.